Hello, math humans. We're going to do 1.10 today. It is our last section of Chapter 1. We're going to be talking about variation and modeling. Our objectives are that we are going to find either direct, indirect, or other varieties or variations of variation models. This is a particular type of problem. And then we're going to do regression models for data. So let's jump right in. Our first type of variation is called direct variation. The equation for this is y is equal to kx. So k is called the constant of proportionality. That is a really long word. Whew. Or if the words in a problem say y varies directly with x, it's implied that as y varies directly, notice varies directly, the y and the x are on the same line, k is always going to be generated. I can find k from the data because it's just going to be y divided by x. If you'll notice, k is also the slope of a really simple line. It just looks like that. So if that's true, then that means that k has to be the same for every different data point along that line. And so that's one way that you know that a problem is direct variation, because when I do y divided by x, I always get the same k value. Alrighty? There's going to be several different types of variation. It doesn't always have to be linear. You could see something that says y varies directly as the square of x. All you really have to know is that when I write this equation, I'm going to get y equals y varies directly. It means it's all on the same line. It implies that there is a constant of proportionality and then x squared. So, and it can even have multiple variables. I could say y varies directly as the square of x and the cube of z. And so then I would just write that equation, and then y would equal kx squared z cubed. So the key thing to notice as a variable varies directly. Ooh, I spelled that wrong. My bad. Got an extra little L in there. When something varies directly, it's going to generate a constant, and I can always solve for that constant by isolating that variable in the equation. All right. So let's just jump in and do some examples. Okay, so for our first example, example 1, I want you to write the related direct variation model. So we're basically just going to write some models, okay? And it's all going to be word problems. So one of the issues in this particular section is that oftentimes I have to write equations from words. So our first part of example 1 is going to say z varies directly with the square of a. And so then I just write what as I read. Z varies directly, and that's how I write it. I write as I read as the square of a. That's pretty easy. B is going to say h is directly proportional. Notice that the words are a little bit differently. So if I have varies directly and is directly proportional, that basically says the same thing to t. So if I wrote that equation, h is directly proportional to t. Anytime you see the words varies directly or directly proportional, or another type of proportional, it's always going to generate this constant of proportionality. Okay, and then the last one I think in this section says A varies directly with the square root of B, and that's not a 6, that's a B, and the cube of C. And I'm just going to do this here. A varies directly with the square root of B, there's my B, and the cube of C. So that's actually not so bad. One, I would tell you that as you do these, you need to write as you read. Varies directly means you're going to have equals and then a K, and then you're going to substitute in all the variables that you're using. So if we have direct variation, we also have inverse variation. Same basic premise, but instead of writing my y equals kx all on the same line, I'm going to scribble it out so you don't get confused. Inverse variation is y is equal to k over x. This is why it's called inverse variation, because now the k is in the denominator. And again, I could solve for k. K is going to be equal to, and I would cross multiply yx. So I'm just going to rewrite this since I scribbled all over it. Okay. The words that you would see on these types of problems, y is inversely, that's a hard word, proportional with x. So the words look just a little bit different with x. So we're going to do some examples, but y is inversely proportional. So instead of saying y is directly proportional, now it says y is inversely, which means put it in the denominator, and that's all it means. The k is always held in the top unless a specific problem told you differently, but k is always going to be in the top. So then let's do an example. So this is our second example, and we want to write the inverse variation model. All right, and again, we're going to do 3 different ones of this. Y is inversely proportional to the square of x. Y is inversely proportional to the square of x. I write as I read. The B one, y varies directly, that was really bad grammar by the way, sorry, as the cube root of x. So I'm going to write as I read. Y varies directly, oops, my bad, this should say inversely, because we've already done directly, inversely as the cube root, so that's going to be the cube root of x, okay? And again, I could solve for k, and I would just cross multiply, so if I were solving for k, this would be y times the cube root of x, and that would be okay. When I report models, I often have to find the value for k and then substitute that into the equation to report my answer. C, excuse me, y is inversely proportional to the log of x, okay? So y is inversely proportional to the log of x. Well, that was pretty easy, okay? So then the next type of variation, so far we have talked about direct variation, and that one was y is equal to kx. Then we talked about inverse. I'll move my paper up in just a sec. Inverse variation, y is equal to k over x. The next one that we're going to talk about is joint variation. And that means that I can have all kinds of craziness going on. So the words might say y varies jointly, and then it would just keep going. And basically, it's a way of bringing in multiple variables. All right? So let's do our next example. So example 3, we're going to write the model. A variation. All right, so for A, I'm going to have y varies jointly as x and z. So again, it's just a way of bringing in extra variables. Y varies jointly as x and z. So you have to assume that they're multiplied together unless it told you something different. And then the B part would be V varies directly, here we go, as the temperature T, and inversely as the pressure P. So now they're combining several different kinds, and so we just write as we read. V varies directly as the temperature and inversely as the pressure. Now, the one thing to notice about problems that have mixed types of variation, there's only one K. If it was a unique situation and it had multiple variables or multiple constants of proportionality, that would have to be stated in the problem. Typically, at our level, there's only going to be one constant of proportionality. All right, the next problem that we're going to do is a word problem. So again, it would be really nice if you wrote the word problem down so that you can have it to reference in the future. So just going to have to bear with me, SYLVA. So in Pennsylvania, the state income tax is directly proportional to gross income. You are working, that's a G, in Pennsylvania. I'm going to just write it as Penn. And your state income tax deduction is $46.05 for a gross monthly income of $1,500. Find, got to scoot the paper up because I'm writing big and sloppy. Find the model that gives the Pennsylvania state income tax, almost done, in terms of gross income. Now, when you have a direct or indirect or any type of variation problem, and it is written as a word problem, the first thing that you should always do is define your variables. So I'm going to say that my state income tax is going to equal Y, and my gross income is going to equal X. One of the things that's often easy to do is like if we look back at this one up here, this is volume is equal to temperature divided by pressure. So sometimes if I have many variables going on, I can just use the first letter of the word, and it helps to substitute values into your equation. So let's talk about this one. I defined it because state income tax, too many letters, so I just wrote Y and X. In this one, it actually asks me to find the model, which means I'm going to have to solve for K. So if I go back up into the body of the problem, I can see that my state income tax deduction is 46.05. I'm going to just put that right there. And that my gross monthly income is $1,500. Okay. Then I'm going to go back up to the first sentence. It says state income tax Y is directly proportional to gross income. Well, now I can solve for K. So K is just Y divided by X, which is 46.05 divided by 1,500. And if you do that math, you get 0.031. And so since the problem wanted us to write a model, then for my model, I'm going to write Y is equal to 0.031X. And then we're done. So it's really not as bad as it would seem. But anytime that you are asked to write a model and you have data, then that means you have to solve for K and then rewrite the model with that data in there. Okay? All right, I have one more word problem for you. Sorry, that's a little bit hard. And then we're going to go back and walk back through a regression problem. The distance that a ball rolls down, that's a down on an inclined plane is directly proportional to the square of the time it rolls. Whew. During the first second, the ball rolls 8 feet. Okay, so in this particular model, or this particular word problem, we want to write the model. All right, and again, in this one, I'm going to have a data point. So this one says the distance a ball rolls. So I'm going to let D equals distance. Remember that when we have a word problem, you always need to define your variables. D is the distance the ball rolls, and then T is going to equal time. So now I'm going to write down what they give me for data. So distance is 8 feet, and time is 1 second. It's also nice to include your units. So now I can write the model. It says the distance a ball rolls down a plane is directly proportional to the square of the time it rolls. So there's my model. I have to solve for K so that I can write an accurate model. So K is equal to distance divided by time squared. So it's 8 divided by 1 squared. So K is 8. So then my model is going to be D is equal to 8 times squared. And then that would be the model for that particular set of information. All right, we haven't done a regression problem in a couple of sections, so we're going to walk back through a problem. I might recommend that you have your note card out that has the steps for regression on it, and then we are just going to walk through that process because the expectation is now you know it and you'll be able to do it forever. So we're going to look at a set of data that has the population in millions. Always important to know what our population units are of the United States from 2000 to 2007. Time is equal to 0 is going to be at the year 2000. Okay? All right. So in this particular problem, we want to find a linear. It's very polite of them to tell us what type of model that we're going to use. Find a linear model and predict the population in 2020. All right, so as we get started on our problem, I'm going to draw our data, try to squeeze it all in on one line. So this is going to be the year, and then this is going to be the population. And remember, this is in millions, which is going to be important when we report our answer. I guess you need to scoot it up so you can see. So in the year 2000, there are 282.4. In the year 2001, there are 285.3. 2002, it's 288.2. In 2003, it's 290.9. In 2004, it's 293.6. In 2000, we're almost done. In 5, it's 296.3. 2006, 299.2, and our last data point, 2007, is 302. And remember, those are our millions of people. All right, so if you'll remember, you have your data written down, so I'm going to kind of cover mine up because I need you to be able to see my calculator. The first thing that I'm going to do is I'm going to do second memory, and I'm going to clear my list 4, and then enter. Then I'm going to turn my stat plots on. I'm going to turn on the first one. Okay. And then I'm going to go and do stat edit, and I'm going to enter my data. Now, if you look back at what I'm covering up with my calculator, it said that time is equal to 0 is the year 2000. So that means that when I enter my data points, let me move my grapher for just a sec, this should be the year 0, 1, 2, 3, etc. when we enter our data. Otherwise, it will change the equation that we get when we do regression. So I'm just going to enter my independent variable first. I'm going to enter the time. So I'm going to enter 1, 2, 3, 4, 5, 6, and 7. And then I'm going to go back in and I'm going to enter all of the data that we wrote down. Enter 290.9. And if you get behind, that's okay. You can pause me. 299.2 and then 302. All right. It is always a good idea to go back and check to make sure that you entered your data correctly, because if your data is wrong, your equation is going to be wrong. And I believe that all of my data is okay. So the next thing that I'm going to do is a zoom 9 so I can look at it. So I could quit. Maybe I'm going to do a zoom 9. 9. Oh, it means that I must have done my data incorrectly. Let's go back and look at my data. Yep, my bad. What did I do? Oh, sad day. So this should have been a 0, 1, 2, 3, 4, 5, 6, 7. Now we're good. So it was saying that the dimensions didn't match, so I had to go back and fix that. So now I can do a zoom 9. Now it's happy. Okay. So now I'm going to do my equation. So stat, calculate. They told us it was linear, and I'm going to store my equation. I'm not sure if my first equation is clear. I didn't check that, so I'm going to put it in alpha F4 in number 2, and then I'm going to hit enter. And then I would write down my equation. So I have y is equal to 2.782x plus 282.5, and my r is 0.999. So my r is really good. All right. So then I'm going to go to my y equals, oh, lucky me, and I'm going to clear that. Now I'm going to graph, and it's going to draw the line. That's pretty slick. Lucky me that I remembered that I had an equation there. And I'm going to do a zoom 3 enter, and I'm going to zoom out because I know that I'm going to need to zoom out a little bit. So I'm going to do second calculate value, and I'm going to put in the year 20. And it tells me, whoo, the light is bad. F of 20 is going to equal 338.143 million people. Okay, all right, and you can't see that, so I'll move my paper up so you can see it. So they asked us to write a model, so this is our model. They asked us to predict what happens in the year 2020, and then I didn't ask this, but a good method or thing to remember is that the model that we chose reflects 99.9% of the data points. Therefore, this is a really good model. All right, another question that might be asked for this type of problem is, do you think that this is a good prediction of the population of the U.S. in 2020? And at that point, I would say maybe not, because my data is 13 years old since it's now 2020. Since my data is 13 years old, the growth may have changed. So I would say we would need to recollect data to make sure that our model is accurate. All right, that is it for today. I will see you soon.